Welcome to Evaluating Fire Risk in Existing Buildings, presented by the National Association of State Fire Marshals, Fire Research and Education Foundation. This course discusses the basic concepts of fire safety assessment and evaluation of buildings. The methods available to conduct these evaluations are layers of fire protection analysis and fire risk indexing. Each method considers the presence of layers of protection, safety layering, and evaluates the fire safety attributes of each building in relation to the risk that the occupancy presents. We'll review two widely used methodologies for assessing existing buildings, Chapter 14 of the International Existing Building Code, and NFPA 101A, the Guide to Alternative Approaches to Life Safety. Each of these documents provide a roadmap for the evaluation process. We can safely assume that a building is constructed in compliance with current regulations. Does the building relative level of safety ever change? Often, the building or its systems are allowed to deteriorate, or unexpected hazards are constructed adjacent to the building. On the other hand, if the building is maintained well and surrounding buildings don't pose an additional threat, then the level of safety will remain stable. However, society's expectations change over time, and it's likely that a building constructed many years ago will not include all of the safety attributes expected in a new building. As time progresses, we gain a better understanding of the hazards presented and develop some new methods to address some of those hazards. Thus, our codes and standards change as we develop new protection strategies. Do existing buildings have to comply with codes and standards? And does the acceptable level of risk ever change? Since codes and standards change throughout the life of that building, do existing buildings have to comply? Not normally. Generally, public policy dictates that a building that was compliant with a jurisdiction's regulations at the time of construction does not have to be updated to later versions of the codes. On a rare occasion, jurisdictions in the model codes identify a risk that is unacceptable, even in existing buildings. These risks are then mitigated using retroactive requirements. These are rare but important events. So does the acceptable level of risk ever change? In other words, does the expected standard of safety change over time? Absolutely. And the change may be to a safer environment, or in rare instances when we actually have seen changes to a more hazardous condition. Let's examine that idea a little deeper. What is the acceptable level of fire safety? Well, it depends on who you ask. One city manager philosophized that if he agreed with the fire marshal all the time, nothing would ever be built in his city because it would all be concrete and steel construction with no combustible contents, and everything would have a sprinkler system. But if he agreed with his economic development manager all the time, the city would burn down because he would have no regulations. His perspective was that the two department heads were a good check and balance system for the community. In most communities, the members of the community should determine the level of fire safety they are willing to accept and are willing to pay for. One problem is that the general public doesn't have a good understanding of fire dynamics, the speed with which fire spreads, and the limitations of responding fire suppression personnel. So they depend upon their fire department personnel to help them with a decision. By doing this, they assume that any building that they are in is safe, and they don't fear that the building will catch fire, or that they will be trapped should a fire occur. The public has a great deal of trust in the fire service, and it's up to the fire service to maintain that trust. The codes and standards organizations attempt to codify the level of safety from most communities in the U.S. You might consider the codes being developed to fit within a bell curve that reflects the levels of safety across the country, so that the model regulations fit most of the communities, but not all. This becomes the de facto minimum level of safety consistent with the national standard. Professional opinions as to the appropriate level of safety are varied as they're professionals. Engineers sometimes are willing to shave the safety factor in fire protection systems, depending upon their mathematical evaluations, than others. Firefighters and fire prevention officers sometimes want absolute safety, which can't be provided. Elected officials are sometimes willing to accept the level of safety that the building owner wants to provide, regardless of regulations or other factors. These are the issues that need to be addressed through robust communications between all stakeholders, and it's important to consider all positions when moving through a fire safety assessment of a building. Fire safety assessments are intended to identify strengths and weaknesses in a building's fire protection scheme. In order to conduct such an assessment, it's important to consider several different factors. One factor is the level of risk that a particular property presents. The risks can be divided into three categories. Risk to citizens in the building or adjacent to the building that would otherwise be affected because of their proximity to the building. Risk to firefighters and other emergency workers responding to an emergency in the building. And economic risk related to the value of the building, the businesses operating in the building, and the economics of the community. When assessing these risks, life safety is paramount. Citizens should be able to depend upon a level of safety that provides them the opportunity for survival should a fire occur, and they take appropriate action, such as evacuating the building. Firefighters should be able to depend upon their training and assessment of a building to determine whether they will conduct interior rescue or suppression operations without unexpected building collapse or other catastrophic event that jeopardizes their safety. If a building is critical to the economic well-being of a community, the citizens should expect that safeguards be in place to avoid that business suffering a loss that would put them out of business or cause them to shift the operations to another community. Any fire safety assessment should start with an identification of the risks associated with the property being assessed. Once we've identified a building's risks, we need to assess its fire safety features. Each fire safety feature can be viewed as a layer of fire protection. Rated construction, such as 1 hour or 2 hour construction, would be a layer. A fire alarm system would be another layer. An enhanced egress system with short egress distances could be considered another layer. As most fire safety professionals know, there isn't one solution for all of a facility's fire and life safety problems. Instead, most facilities will need several components or layers of fire protection to achieve the desired level of safety. Some safety layers provide greater protection than others. Sprinklers are widely believed to be the best engineered solution, but 2 out of 3 of reported fires in sprinklered buildings don't grow large enough to activate the system. So are portable extinguishers a needed layer of protection in a sprinkler building? The data would seem to indicate that they are. Some safety layers cost more than others, and with a finite amount of funding available for the construction and maintenance of buildings, it's important to attempt to identify the most cost-effective solutions to the identified risks. It's necessary to conduct a comparative analysis of utilizing different layers of fire protection to achieve the desired level of safety. This comparison can be somewhat difficult and subjective using the current knowledge and tools available. All of this leads us to the real question: how much is enough? We can probably agree that a sports arena seating 50,000 fans needs a higher level of protection than a remote unoccupied telephone switching station. But how much more? How much do they cost? And which layers are most effective? Each fire protection feature creates another layer of protection. Combining several layers of safety will usually have a cumulative effect both in the level of safety and in cost. Quantifying those effects may be extraordinarily difficult. On the other end of the spectrum, can we have too many layers? Will some fire protection layers interfere with the facility's operation and what they cost? All of these considerations should be taken into account when developing or evaluating the overall fire safety scheme for the facility. The goal is to identify the appropriate level of safety, then utilize the most cost-effective methods available to achieve it. While our model codes and standards have definitive prescriptive requirements to achieve a particular level of safety, there may be alternative equal or superior methods to achieve an equivalent level of safety. There are a number of models that can be adapted to fire risk analysis. 2 models that are used in other industries include quantitative risk analysis and process hazard analysis. Process hazard analysis is widely used in assessing risks to manufacturing or hazardous processes, and quantitative risk analysis is used in many fields, including the financial markets. LOPA, which is an acronym for Layers of Protection Analysis, is one of the tools used in process hazard analysis that can be modified for use in fire risk analysis. A simpler method than LOPA is fire risk indexing. In this model, values are assigned to various protection components or layers, and some have pass-fail criteria based upon the overall score given of a facility. We will focus on LOPA and fire risk indexing in this presentation. LOPA is very complex. Many times it uses fault tree analysis and other mathematical models to determine failure rates for components and systems. The results of these exercises are as good as the professionals conducting the exercise and can be very accurate and enlightening. LOPA works by identifying the protection components or layers, assessing the value of each. Then it evaluates the synergistic effects of the layers to determine the overall value of the protection system. Finally, LOPA compares the value of the protection system to the acceptable level of risk for the building. While we've mostly focused on the protection layers that inhibit fire growth or suppress a fire after it starts, another critical part of the analysis is the mitigation techniques that are built into the building. For example, arc fault interrupters and high limit switches on equipment. All of this must be considered to gain a clear picture of the risk. Because of the degree of complexity attached to LOPA, fire risk indexing models have been developed. These models are far simpler and provide a level of analysis that is acceptable for most projects. Fire risk indexing uses performance such as its guide for assessing risks. Typically, the tool contains set values for different layers of protection. These values have been developed by experts in the field through an evaluation and discussion and are usually accepted as being relatively accurate predictors of performance. While the indexing tools are easier to use because of the values that are already provided, they aren't able to evaluate the synergistic effects of the different layers as well as some other more complex models. The most widely used fire risk indexing models are NFPA 101A and Chapter 14 of the International Existing Building Code. Codes and standards use safety layering in their design. For instance, a warehouse with high piled combustible storage may be required to provide smoke removal or smoke and heat vents, add draft curtains, add sprinklers, and add firefighter and fire apparatus access. These are all separate and distinct layers of protection, and together they provide the level of safety envisioned by those authoring the code. The codes and standard development process, however, doesn't provide for a thorough risk assessment before adding or deleting requirements. This is especially problematic when one industry promotes the use of one layer at the expense of another to make the new regulation more cost-effective. During code development, many take a quick guess at risk assessment. More scientific methods would be welcome. Take our warehouse scenario, for example. Some believe that smoke and heat vents have a detrimental effect on the operation of sprinklers, but if the sprinklers don't operate effectively, interior fire suppression operations may be impossible without the vents. The issues have been debated frequently in the code development arena, but little scientific evidence from fire testing or other methods have been made available to the decision makers. Codes and standards are intended to establish the minimum level of safeguards for buildings and facilities. Some communities will add requirements to make them safer, and a few will remove requirements that they believe are unnecessary. So let's look more closely at the safety layering concept and our codes. Layers of safety can be divided into four general categories: prevention, activation, active suppression, and passive prevention. Prevention layers prevent a fire from starting. Prevention is always the best outcome. A couple of the layers that contribute to prevention include arc fault interrupters and the isolation of ignition sources. Activation layers require human intervention to activate fire protection features. Features requiring human intervention include portable fire extinguishers, manual fire alarm systems, and similar features. Active suppression layers actively prevent the fire from spreading. Active fire protection refers to automatic fire suppression systems, including sprinklers, kitchen hood systems, automatic fire alarm systems, automatic closing fire doors, etc. Active systems are very effective, but require regular maintenance to ensure that they will operate as intended. Passive prevention layers passively prevent the fire from spreading. Passive fire protection includes rated construction, fire barriers, fire walls, and other construction features that do not require mechanical or human intervention to perform their function. It also includes distance requirements implemented to ensure that buildings are constructed at a safe distance from one another. These features have proven very effective, but require regular inspection to be sure that they haven't been compromised. If we consider general safety requirements, some of the issues might be: where can I store hazardous materials? Can I store them next to ignition sources? How many hazardous materials can I have in a room? What quantity of flammable liquids can I place in a container? Do I need to secure that compressed gas cylinder? We also must consider components associated with means of egress, such as: which way do the exit doors need to swing? Do I need panic hardware? Do I need exit signs? Do I need egress lighting? Can I utilize delayed egress? What's my travel distance? Fire detection systems are another safeguard that can go into a building. Fire detection systems are going to detect a fire and provide for early warning along with the fire alarm system, which will provide the early warning, giving people more chance to safely egress the building. And with fire suppression, we're actually going to fight the fire automatically as people are exiting the building, providing protection to the occupants, providing a limitation on the size and spread of the fire with our suppression system. Fire resistive separations separate one occupancy from another, or one use from another, or one floor from another. Fire resistive construction assists in limiting the fire spread in a building. Are there other safeguards that provide additional layers of safety in the code? Absolutely. There are many, such as interior finishes on wall surfaces. What's the flame spread rating? So not only are we looking at what's the fire rating of the wall, what's the flame spread rating on the covering on that wall? So we're looking at many things in the code dealing with additional layers of fire safety in a building. To illustrate how this concept works, let's examine the layers of protection of an office building required by the International Existing Building Code. We begin with a 4,000 square foot office building and apply Type 5B construction to it. Type 5B is the least restrictive building type. If you can build it and make it stand up, you can use it. Since this building is 4,000 square feet, the building is allowed an occupant load of 40. An occupant load of 40 requires one exit. Yet if we compare that to a larger office building, such as one with 20,000 square feet, the type of construction would need to be enhanced to a greater fire resistance level, Type 5A. The occupant load increases to 200, which requires 2 exits and fire sprinklers. When we increased our building size, we added additional exiting, increased fire resistance level of the type of construction, and added fire sprinklers. These additional layers of protection are required because of the increase in size and the increase in the number of people in the building. Now consider a 2-story, 50,000 square foot office building. It applies Type 3A construction. This building allows us to have an occupant load of 500. As a result, this building requires 3 exits, a fire sprinkler system, and a fire alarm system. When we compare the 4,000 square foot office building to the 50,000 square foot office building, we see that both are used for the same purpose, an office, but we've increased the fire resistance rating of the construction and the number of exits. We've added fire sprinklers and we've added a fire alarm system. All of those are layers of protection added to the building. As the size of the facility changes, the risks change. Each additional layer of protection is added to mitigate that increased risk. Consider the layers of protection in the International Fire Code. A great example is Class II combustible liquids. What are the fire safety features that would be associated with Class II combustible liquids? For up to 120 gallons, the fire safety requirements are that it needs to be in an approved storage container in an approved location, so the basic building features are considered adequate if the liquids are stored properly. If storage of up to 240 gallons is needed, fire sprinklers can be provided and the increase is allowed. We can also add an additional layer of protection in the form of approved liquid storage cabinets. Now the added quantity increases to 480 gallons. If more than 480 gallons is needed, Separate fire compartments called control areas can be built to gain another increase. Each control area can now have up to 480 gallons, and a building is allowed up to 4 control areas for a total of 1,920 gallons of Class II liquid. We haven't changed the classification of this building, and we've gone from 120 gallons to 1,920 gallons by adding several layers of protection. Beyond 1,920 gallons, the code would require the building to be a Group H occupancy, which has even more protection requirements. The LOPA analysis is specific to hazard scenarios. As we previously discussed, it should always be based upon a specific desired outcome. That is, if we don't know where we're going, how do we know when we've arrived? And when the LOPA analysis may or may not assign a specific value to a protection layer, it does consider the effect of each layer and the combined value of the overall protection scheme. The analysis should clearly show that the total values of the layers will lead to the desired outcome should a fire or other disaster occur. Because of the complexity involved in LOPA, it is difficult and nearly impossible to codify a building. Therefore, some of the codes and standards implement fire risk indexing as an alternative method. Currently, NFPA 101A, Guide on Alternative Approaches to Life Safety, is an evaluation of existing buildings that utilizes a fire risk indexing process to evaluate a building's hazards and level of life safety. Additionally, the International Existing Building Code, Chapter 14, deals specifically with performance compliance methods where a building is evaluated using a fire risk analysis based on its fire risk indexing. Because there are a variety of safeguards, it can be difficult to assess a building's fire safety in a uniform and consistent way. Fire risk indexing simplifies the LOPA concept by assigning values to different safety layers. A building is assessed in accordance with a particular indexing model, and the aggregate values of the protection layers are used to determine whether the building meets a predetermined level of safety. The two most widely used models, NFPA and IBC, attempt to include many of the various safeguards that have an impact on the level of safety. The fire risk indexing provides a ranking method or a scoring method for each of the various mitigation features. Through that specific ranking or scoring, you can provide a process that is repeatable. For example, we ask 6 different people to assess a building using a fire risk index. The evaluation may include, is there a sprinkler system? Is there a fire alarm system? Do the exits comply with the current code? A plus or minus score for each of those components is entered on a worksheet. At the end of that evaluation, and at the end of the survey of that building, you add up the score. Based upon that score, the level of fire safety in that building can be established. Again, one of the advantages of fire risk indexing is it is repeatable. LOPA, however, is more subjective. And because different people look at some of these issues differently, it's likely that each analysis will result in a different outcome. The ranking in this fire risk indexing provides the ability to develop a relative fire risk where we can compare different buildings, and it is repeatable. Fire risk indexing is not a new concept. It has been around for a number of years, used by a number of industries. Probably the one you're most familiar with is the ISO rating for home insurance, known as the Property Protection Classification. Each property is evaluated based on the fire safety attributes of a community. For instance, what are the capabilities of the fire department, available apparatus, equipment on apparatus, response times, etc. What is the capability of the water supply in relation to the buildings in the community? Based on all of the ISO criteria, you can determine the property protection classification, which becomes a component in calculating the insurance cost for a particular building. It's a numeric process and is very easy to repeat, very consistent, and it works for the insurance industry. Another valuable example of indexing is the Glasgow Coma Scale, widely used to determine the brain impairment associated with an accident or other brain trauma. The layers in the Glasgow Coma Scale are the function of the eyes, speech, and motor skills. Each layer is assessed and given a numerical score of 1 to 6. Once each score is tallied, they are added up to determine the level of brain impairment. In this example, the victim opens her eyes in response to someone talking to her, a score of a 3. But she is not able to talk, and the sounds emanating from her are incomprehensible, a score of 2. She is not able to obey commands, but will flex or withdraw to painful stimuli, a score of 4. The total score of the 3 layers is 9, which, according to the scale, is in the moderate range of injury. This evaluation meets the goals of being relatively easy to use, providing consistent results, and being highly repeatable. These are the same goals we want to see in a fire safety indexing system. Other indexing applications include many that are used in industry. Dow's Fire and Explosion Index, which is one of the most common process hazards analysis indices that's been specifically developed for the chemical and process engineering field. The MOND Fire and Explosion and Toxicity Index, which deals with specific material hazard factors and includes quantity factors based on inventory of material and actual storage configuration of the material. There is a wood frame apartment building risk analysis, which evaluates the risk assessment in existing wood frame apartment buildings. A specific fire risk index for historic buildings, developed by John Watts and Marilyn Kaplan, has been used to evaluate how to maintain life safety in historic buildings and still maintain the historic quality of those buildings. We use indexing in wildfires. We evaluate archaeological sites. We determine fire spread indices. We do wildland fire planning based on indexing. What's the slope, the temperature, the type of fuel, the wind speed, and all of those criteria go into an index to determine planning criteria for wildland firefighting. In addition to full-blown engineering assessments, there are widely available tools to utilize that simplify the process. When we are looking specifically at fire safety assessments, some of the available tools include code narratives, code descriptions, code commentary, and handbooks that provide explanations of the requirements and provide examples and guidance on how to apply the requirements. Checklists have been developed to review each of the layers of protection. Fire risk indexing provides a relatively simple mathematical analysis of the level of safety in a building. One thing all of these tools have in common is that the use of layers of protection to achieve the stated goal. Fire risk indexing is a technique for evaluating alternative fire safety configurations in existing buildings that is intended to provide a level of flexibility to the designers in order to identify the fire protection schemes that best suit the situation. The numerical values assigned to the indexing parameters are mathematically manipulated to create a single expression or a single result, which provides the overall level of fire safety for the building. Interestingly, in 1924, NFPA Building Exits Code was proposed at that time, and it included level of risk indexing. An excerpt from that code says the relation between the maximum number of persons on each floor shall be determined by a specific formula. Let's look at that formula now. It will provide a clear example of the relationship between a few different safety factors. This formula was proposed for inclusion in the Building Exits Code, which is now known as the Life Safety Code. In this formula, the number N equals the number of persons permitted on each floor above the first floor. A represented the number of units of stair width, which 1 unit equals 22 inches. And B represented the type of construction of the building. For ordinary construction, B equals 4. For mill or fire-resistant construction, B would equal 5. You can see that the type of construction and the stair width are two important factors for determining how many people are permitted above the first floor in a building. The C in that equation identifies the protection of the vertical openings. If there were open stairs or unenclosed stairs, the value of C would be 2. If the stairs were enclosed, but there were other vertical openings that were not protected, C would equal 4. If the stairs were enclosed and there were no other unprotected vertical openings, then C would equal 5. This factor recognizes the importance of protecting vertical openings, as fire spread is known to travel most quickly through vertical shafts. The D in the equation represents automatic sprinkler protection. If the building is sprinklered, we get a value of 2. If the building is unsprinkled, there is a value of 1. The E in the equation represented horizontal exits. If there were no horizontal exits, then E would equal 2. If there was one horizontal exit, E would equal 3. If there were 2 or more horizontal exits, E would equal 4. This factor recognizes the value of protected egress from a space. The F in the equation represented the risk associated with the type of occupancy. Low hazard occupancies, F would equal 3. Moderate hazard occupancies, F equals 2. And then for high hazard occupancies, F would equal 1. Finally, all of those components are multiplied together and then divided by H. H is the height of the building measured in stories. As you can see from this example from 1924, fire protection professionals at the time recognized myriad layers of fire safety and rated each layer based upon the judgment of the value of that particular layer. Here is an example of how the formula is applied. Take the 2-story building we used earlier, 50,000 square feet total, 25,000 square feet per floor. In this case, A, our units of exit width, consists of 2 stairs. Each stair is 44 inches wide, providing 2 units of exit width in each stairway. So we get a total value of 4 for the value of A. B, the type of construction in this case, is ordinary construction. So enter a value of 4. C is the value for vertical openings. Assuming unenclosed stairs, which is allowed under this scenario, connecting 2 stories in the building would provide a value of 2 because the stairways are not within a rated shaft. D receives a value of 2 because sprinklers are installed. In this example, there are no horizontal exits, so enter a value of 2 for a factor E. And because this is a low hazard building, enter a value of 3 for factor F. Finally, H, the height in stories, is a value of 2 for 2 stories. So now the formula reads N equals 4 times 4 times 2 times 2 times 2 times 3 divided by 2, or 384 divided by 2, which is 192. This is the number of people allowed on the second floor of this building. Again, this is a simple indexing formula created 90 years ago by experts at the time. There is still a great deal of validity in the concept, and we will be taking it to a new level soon. Consider the level of safety provided. We look at what types of safeguards were included in the building. These are components of fire safety that we can use an indirect or direct measurement to determine if it is or not provided. These are often called parameters or index parameters within the building, similar to layers of protection, or some could actually be called components of layers of protection. But these safeguards are what we will evaluate to determine what the level of fire safety is when using our fire index. Some of the safeguards that we'll evaluate in our index. What's the building's height? The higher the building, the greater the risk. What's the building's area? The larger the building, the greater the risk. Are there vertical openings? And are those vertical openings protected or unprotected? Unprotected openings increase the risk. Is there an automatic suppression system or sprinkler system provided in the building? Automatic suppression is often used to offset some of the risk. Are portable fire extinguishers provided? Fire extinguishers give occupants a chance to extinguish a fire while it is still small, many times avoiding major fires. How many exits are provided, and what's the exit width that's provided? The more exits, the wider the exits, the greater the opportunity for people to escape an emergency, thus reducing the risk However, the exits need to have adequate separation to be able to serve all of the occupants of the building. If exits are too few, too narrow, or consolidated in one area, the risk would be greater. Which direction do the exit doors swing? Doors swinging opposite the direction of exit travel create significant additional risk, because people exiting the building can easily become crushed against a door that swings inward. What's the maximum travel distance within the building? The shorter the better from a safety perspective. Is there a fire alarm system providing notification to the occupants? Is there a fire detection system providing early detection of a fire? Does the building provide compartmentation or fire separations? Does the HVAC system provide any benefit or smoke control, or will it spread smoke and toxic gases throughout the building? Are smoke detectors included in the HVAC system ductwork to shut down the units when they are conveying smoke? Is there a smoke control system in the building? Are there dead-end corridors that could result in people unfamiliar with the egress routes being trapped in an emergency? What are the interior finishes in the rooms, in the corridors, in the stairways? What's the occupancy? An office represents less risk to occupants than a nightclub. Are the elevator controls up to code? Can the elevators be used for fire department access? Are the elevators captured and taken out of service so we don't put occupants in jeopardy? Are exit signs provided? How about emergency lighting for exit pathways? Are there any other special hazards that we need to address and consider when looking at this particular building? Given the number of available layers and the fact that they all have different costs, both in dollars and operational efficiencies, it's worth asking the question, how many layers are needed? Which ones provided the greatest value, the biggest bang for the proverbial buck? Can you rank these features according to their value to the overall fire safety of a given building? Maybe sprinklers are at the top of the list, but fire-resistant construction will allow interior fire suppression operations should the sprinklers fail. Fire separations will allow protect-in-place strategies where needed, and a smoke exhaust system will add to the allowable egress time. All have a role to play depending upon the building or facility being protected. In order to quantify the different components or layers of safety, it's necessary to compare the value of one against the other. So let's look at fire sprinklers and smoke exhaust systems. Do they provide an equivalent level of safety? Most would answer no. The sprinkler system is more dependable, is designed to control or suppress the fire, while the smoke exhaust system is only intended to remove smoke from the building, which enhances egress time, but does nothing to control the fire. They both provide a benefit. Do we give them equal ranking or equal scoring? Of course not, because that level of benefit varies between each of the various components. When considering a smoke exhaust system, where does it provide the greatest benefit? Fire safety or preventing fires? The smoke exhaust system does nothing to prevent fires or control the fire, so its value is virtually zero when judging its ability to prevent fires. The greatest benefit provided by smoke exhaust systems is the fact that they will increase the time for occupants to exit the building, so it definitely impacts the means of egress or time to egress. Smoke exhaust systems are called out in warehouses primarily to enhance the ability of fire suppression forces to operate within the building effectively. While there is some debate as to how effective these systems are, it's widely accepted that fire suppression activities are made significantly more difficult when copious quantities of smoke are present, making observation and movement more difficult. So when we consider the ranking and scoring for a smoke exhaust system, it will receive a different value based on the general category being evaluated, and would therefore receive the greatest score with regards to means of egress. So how do we put a value on these safeguards? Fortunately, the existing indexing system provides us with the values of many components of fire protection. The fact that the numbers are provided and predetermined allows for repeatability of this process, allows for consistent results of this process, and allows for a very real and practical comparison between the two buildings. And in fact, can allow for a comparison of, for example, if sprinklers weren't provided in this building. How would the value change? Are there other layers that could be added to achieve the desired result for less money? A study of the values assigned to different components by the IEBC and the NFPA provides an understanding of which components provide the higher, more valuable levels of safety. If someone installs components or layers that are not included in these documents, it's important to give careful thought and consideration to the relative value of those. Fire risk indexing theory is based on quantitative risk assessment. While qualitative analysis is used to gain a broad and conceptual understanding of a fire protection scheme, the quantitative analysis actually provides a definitive evaluation using numerical data and usually a pass-fail criteria for a given facility. Comprehensive fire risk analysis theory uses aspects of management science and design analysis, which is a very well-established process. The fire risks of the building are evaluated using a multi-attribute decision-making process. The mitigation components are then evaluated against the risk profile, and a report is generated detailing the results of the comparison. The building may then be deemed to meet the needs outlined in the beginning of the exercise, or the analysis may indicate additional layers of protection are needed. This process is a quantitative analysis. The good news is that ready-to-use fire risk indexing tools are available that have already undergone substantial study and debate in determining the values and numerical components of the formulas used. Essentially, the fire risk indexing simplifies the broader theories associated with fire protection analysis and provides a useful series of calculations to use in the field. The quantitative analysis has been simplified into a qualitative analysis where you can insert values based on answers to questions. You don't have to be a fire protection engineer to use an indexing tool. The fire risk indexing process parameters and values are available in IEBC Chapter 14 under Performance Compliance Methods and NFPA 101A as a fire safety evaluation system. Both are established and tested methods that provide a relative ranking or scoring for each safeguard or each parameter. Credible comparisons can be made between buildings within each system, however. Credible comparisons cannot be made using the different systems. For example, comparing buildings using either the IEBC or NFPA, but mixing the two will not provide helpful or consistent results. Fire risk indexing evaluates safeguards in three categories: fire safety, means of egress, and general safety. When assessing fire safety features, we check to see if different hazards are separated, if fire sprinklers are installed, or examine the type of construction. Means of egress evaluations include exits in terms of amount and size. In addition, it may ask if any dead-end corridors are provided or identify the maximum travel distance. In the last and most broad category, general fire safety, we review items such as interior finish and flame spread requirements, vertical openings, and their fire protection, and fire alarm systems. Both the IEBC and NFPA evaluate buildings within these same three categories. It is important to know that while we may not be able to assign a particular attribute to one of these categories, most often the attributes overlap between categories, so the categories aren't really critical to the utilization of the indexing tool. In the IEBC, the evaluation is specific to certain fire safety parameters, which are scored based on their impact to each category. As a result, the following questions are asked. How do fire sprinklers improve the level of fire safety? How do fire sprinklers impact the means of egress? And how do fire sprinklers enhance the level of general safety? Remember, many of the fire protection components will overlap one or more of the categories, and the score for each attribute will reflect the relative value of the component in each category. When all of the components are evaluated, the score for each category will be compared to that in the code to determine whether the fire protection scheme meets the minimum fire safety criteria for existing buildings. Let's consider our two-story, 50,000 square foot office building with 25,000 square feet per floor. When using IEBC, the building must meet the minimum mandatory safety score at the end of the evaluation. In this case, the building is a Group B occupancy, where the building must also meet a fire safety rating of 30, means of egress score of 40, and a general safety score of 40. If the building meets or exceeds the minimum scores in each category, then the building is considered to meet the acceptable level of fire safety. However, it does not mean that it complies with the current code. It meets the minimum acceptable level of safety for that existing building. The minimum acceptable score must be met in each category. While a building might achieve excess points in one of the categories, it still must meet the minimum in the other two in order to be deemed compliant. Using NFPA 101A is similar to using IEBC in that it uses a scoring system to determine the overall level of safety in a building and compares that score to a predetermined level that a committee has deemed appropriate. It also uses three categories to describe components: fire control, means of egress, and general fire safety. As with the IEBC tool, the risk and the mitigation components are scored. For instance, a negative score may be given to a building with unprotected vertical openings, and a positive score will be given for a rated enclosure. There are also criteria listed in NFPA 101A that are simply yes or no. These are considered pass-fail criteria with no numerical value, but the building must have certain safeguards. For components that are scored, each is given the appropriate positive or negative score, then aggregated in the appropriate worksheet to determine if a particular category is compliant. Then the worksheets are compiled to determine if the building meets the minimum requirements of NFPA 101A. To clarify, the scores must be achieved in each of the categories. While a building might achieve excess points in one of these categories, it still must meet the minimum in the other two in order to be deemed compliant. We'll apply the same scenario for NFPA 101A, a two-story office building, 50,000 square feet, with 25,000 square feet per floor. NFPA 101A provides different parameters for existing and new construction. In this evaluation, we'll use existing building criteria. The height of the building is one of the basic criteria upon which all of the requirements are based, and is measured in stories. In this case, a two-story building requires a fire control score of -1 or higher, a means of egress score of 0 or higher, and, for general fire safety, a value of -1 or higher. In this building, with a construction type of unrated combustible, its construction score is -1. If its stairs are not enclosed, the score for vertical openings is a -2. These two items alone would cause the building to fail. The score would be a -3, and the mandatory minimum requirement is -1. So mitigation measures must be considered. In this case, enclosing the stairs with 1 hour construction changes the vertical opening score from a -2 to a 1, which changes the total score for these two components to 0, which is compliant. Meeting the minimum requirements of 101A does not mean it complies with the code for new construction. The approach is different for both the NFPA and the IEBC method. Which method should you use? Either. Both methods evaluate specific safeguards and identify a value for that safeguard. Both methods also provide an evaluation of the combined level of safeguards in existing buildings, and both methods will work as a standalone evaluation. You will come up with different values in each process. You cannot compare the values of one to the values of the other, but when you select one approach, you go through that approach and determine the level of acceptable safety in that building. Neither method is right. Neither method is wrong. Two different approaches to solving the same problem. While both the IEBC method and the NFPA method are equally valid, the NASPM Fire Research and Education Foundation has developed a computer application to assist you in working through the existing building evaluation process. The app is based on IEBC Chapter 14 with an eye toward usability in simplifying the building evaluation based on the specific criteria required in Chapter 14. The app guides you through the process. Step by step, the app will ask for information about the building, such as, is the building protected with a fire sprinkler system? Does the building have a fire alarm system? You provide the appropriate data from your building review. The app will compile all of the data and provide an output as to the safety rating of the building. So in summary, we have looked at basic concepts of fire safety or fire risk assessment as a method to determine the level of fire and life safety in any given building. These assessments are important in determining a community's overall fire risk. An important concept in providing a safe environment is redundancy, which we refer to as safety layering. Because there is no single fire safety component that addresses all of the fire risks completely, it is necessary to provide several layers of protection to achieve the goal. The greater the risk to people or property, the more layers of safety are needed. Fire risk indexing is a simplified method to assess the overall risk in any given building. A number of ready-to-use tools are available for this purpose, and each tool provides a means to compare the level of safety in one building to another and to determine whether a building provides a particular level of safety. In this course, the two most common fire risk indexing applications have been described. Those are contained in the International Existing Building Code, Chapter 14, and NFPA 101A. While these tools use different scoring systems, the concepts are virtually identical. A building's risk and mitigation measures are given either pass-fail or numerical scores. Those scores are then compared with numerical values that have been developed through a consensus process and deemed to provide an overall appropriate level of safety. We have only considered existing buildings in the presentation, but both NFPA and the ICC provide prescriptive and performance criteria for new construction as well. On behalf of the National Association of State Fire Marshals, Fire Research and Education Foundation, we thank you for your time.